Welcome everyone to another session of our Energy and Environmental webinar series. Today we are very happy to have Professor José Torero. He's the head of the Department for Civil, Environmental and Geomatic Engineering at José L. And he will be talking to us about optimizing energy, environment and safety in the built environment. With no more delay, well, I would just like to tell you that if you have any question during the talk, you can post it to the Q&A box that you can see in the bottom part of the of your screen, and we will be asking them to Professor José Torero at the end of the session in the Q&A. Also, if you would like, not just sending it to the chat, but if you would like to say it to ask directly, we will give you the opportunity for that as well. So thank you very much for agreeing to joining us, Jose, and the floor is yours.
Okay, thank you very much. So I'm going to touch on the subject of safety in the built environment, and in particular, I'm going to be talking about fire safety. Now, you will ask yourselves, what does this concern, aspects like energy, for example, and why is it important to address these things together? Now, clearly, we recognize that the built environment is one of the largest energy consumers right now globally. Not only that, it is a subject of massive amounts of embodied carbon. And in general, it is one of the key targets if we want to achieve or approach a net zero carbon economy. So being able to address the built environment in a way such in which we optimize the use of energy is a fundamental aspect of the net zero carbon agenda. So environmental proponents are pushing very, very strongly for ways by which we can reduce embodied carbon. And for example, we're talking about tall timber buildings, for example. Why tall timber buildings? Because they're made out of timber, and therefore they have a negative embodied carbon. And also, when we're talking about tall buildings, that reduces the distance that people have to commute, and therefore it reduces energy consumption as part of transport systems. And clearly, this is a very, very important issue that needs to be addressed. Now, in a similar way, the use of energy in the built environment for heating, for air conditioning, is a key component of the energy that we consume as a society, and therefore making sure that we manage that energy consumption in an appropriate way is a key aspect of building design, building maintenance, retrofit. For example, today in European cities, we have a predominance of existing heritage buildings, and those buildings were not designed on the principles that we are trying to advocate today, and therefore their consumption of energy is very high and needs to be considered in a very careful way. So retrofit has become a mechanism by which we are constantly upgrading our building stock to try to reduce energy consumption. Now, the problem with all these things is that the drivers are extremely strong. So clearly we have a very strong agenda. We have events like COP26 where we are going to be pushing, incentivizing, subsidizing different technologies, different approaches that are going to help us achieve these objectives for the built environment. The question is, are those drivers and their strength potentially also a problem? What happens if we designed a building inappropriately? because we are not paying attention to other aspects of building design. The drivers are so strong that our efforts when it comes to other aspects of building design might not be consistent with the evolution of technology. So what I'm going to be talking about is one of those conundrums, where you have a very, very, very strong environmentally driven driver, which is energy, the reduction of energy consumption, and creating a situation by which the mere fact of introducing these mechanisms to reduce energy consumption resulted in the creation of a fire safety problem. And this came to heads in June 14th, 2017, with the Grenfell Tower fire, as you can see in the image in this slide. So I'm going to be discussing in the context of the Grenfell Tower fire, this conflict between drivers and constraints, when it comes to the design and implementation of the built environment. So here's a paragraph from the report of Sir Martin Moore-Bick. Sir Martin Moore-Bick is the chair of the Grenfell Public Inquiry. And this Grenfell Public Inquiry has been going on already for more than 2.5 years. And it produced a first report, which was a phase 1 report that addressed the events of the night. And right now is in the process of finishing up testimonies or evidence for a phase 2 report, which is going to be providing recommendations on the future of the built environment. So as you can read from that slide, you can see that the problem that is being addressed is a very complex problem of an extremely large fire that spread at a rate that was extremely significant, and it spread burning debris, to fall, around to the point that Sir Martin Moore-Bick defines this as profoundly shocking. So to any onlooker, those first few minutes must have been truly terrifying, which is exactly the case. And it is not surprising that there were desperate shouts from the crowd below as the flames began to take hold with such ferocity. So this event seems to be a very challenging situation for fire safety. And it's important to really understand how we got to this position. Now, as you can imagine, the repercussions of this event are very, very wide-ranging, and they challenge in many ways the perception that we have as scientists in regards to our responsibility to making sure that these things do not occur. So if you think about this particular event, you will realize that the outcome of this event was the death of 72 people. Now, this is something that we can really not take lightly at all in an event of this nature. And in particular, because there is a very unique element of it that is associated to social equity. And people have highlighted many aspects of this particular building. And one of them that has been very strongly pushed is the particular demographic of buildings of this nature. So the residents of the Grenfell Tower are very typical of a modern British metropolitan working class. And the nature of this metropolitan working class is generally very ethnically diverse, with many families, from a broad, potentially refugees or people that have, very poor means. And more than 50% of the people were ethnic minorities living in households that were earning below an average income. So when you think of this problem, you have to think of it in the context of the population that it is affecting. And what are the mechanisms that we're putting as a society to try to protect those individuals? Particularly, what is our responsibility as individuals who are creating technologies, who are creating technical knowledge and diffusing or disseminating technical competency when it comes to providing the necessary equity for these populations that rely on these activities to guarantee their safety. I think we really need to be conscious that there is an element of vulnerability that is associated to the type of populations that generally are affected by this type of events. So if you think about it, that question has come up and here's just one example of journalists raising the question, whether this type of event will actually happen in an affluent community. So we need to really understand what is our role in making sure that when we develop our science and our technologies, that actually we are not creating a situation by which we are unintendedly negatively influencing equity. So I wanted to raise that and just put it on the table because I really think it is very important, because scientists have grappled with the issue of science for the benefit of society for a very long period of time. I mean, clearly there is no matter that raised more controversy about the role of science than the development of nuclear weapons. And you can see from that sentence by Robert Oppenheimer that really this is a moral issue that we have to take into account, because we do have a certain element of responsibility. So, as Oppenheimer says, we have raised again the question of whether science is good for society, or whether it is good to learn about the world, to try to understand it, try to control it, to help give the world increased insight, increased power. Because we are scientists, we must say an unalterable yes to all these questions, because it is our faith and our commitment, that is seldomly challenged, that the knowledge is actually good in itself, because knowledge has power that comes with it. So effectively, we do have a role, and we have to be careful that we actually exercise that role in an appropriate way. But this is particularly important in this space, because what we do have is science against science. And we really need to understand that there has to be an appropriate balance of that science to make sure that this type of events don't happen. So let me go into the particular problem and try to give you an example of why this is such a controversy and this is such an issue that pertains the ultimate ethics of scientific behavior. So this is a video from 1974. And it is an event that happened with the Andraus building in Sao Paulo, Brazil. And it was very representative of a period of time, where many of these events happened. So if I just show you a bit of the video, you will see the type of event that occurred in Sao Paulo. This event actually inspired a film called The Towering Inferno, and shows the propagation of a large fire along a high-rise building, burning multiple floors at the same time and costing the lives of many people. Now, this particular event was not a novelty. This was one of many events that happened in the period that led to a very significant amount of fire research that eventually resulted in the solution of the problem. So by the end of the 1970s, a massive investment had been done on fire research by organizations like the Building Research Establishment, used to be called the Fire Research Station at the time in the UK, BRI in Japan, the Building Research Institute in Japan, the National Bureau of Standards in the United States. In the United States, there was even a Congress act called America Burning that put a very significant amount of funds to try to support the development of methods to try to prevent this type of event. So if I think of this now, we actually solved the problem completely. And this is an example of a late 1970s design that shows you how we solved the problem. So we managed to guarantee that our construction methods, the way in which we built buildings, resulted in a drastic change that guaranteed that no fire will exit the floor in which it was originated. So as you can see from that image, this was an image of the World Trade Center 7. This fire actually burned for 8 hours and progressed or traveled around the entire building in multiple floors that were ignited by the debris of the collapse of the World Trade Center Towers 1 and 2. But it never progressed vertically. It was maintained, within a single floor, thus showing that even in extreme conditions where you have multiple fires that have been started by a major event like the collapse of the World Trade Center Towers, the fire actually never progressed vertically. In other words, the containment of the fire to one floor, was successfully achieved. So we had solved the problem. Now, all of a sudden, we enter the 21st century, and a problem that was solved becomes followed by a series of endless failures that are culminated on the Grenfell Tower fire. As you can see, there's many buildings that burned. This is just a very, very, very small sample and of potential of fires that happened in the years that preceded Grenfell. So Grenfell in itself was a perfectly foreseeable event in the sense that there was plenty of precedent of 5 to 10 of this happening literally every year in different continents, in different countries, under different regulatory regimes. They were all very different in characteristics, but at the end, the problem that we had solved, now we were failing on solving. And the question is, how did this happen? Now, more significant and actually more terrifying is the fact that even after more than 4 years of Grenfell Tower, these fires continue to happen. And we don't seem to be able as a society to actually stop them. So here again is a very small example, sample of fires that actually have happened post-Grenfell, where the latest one happened in Milan no more than 2 months ago. So as you can see, this is a problem that not only we lost control, but actually even today, we have no idea how to fix it. So we need to be able to really understand that there is something that has escaped from our hands here. So a question that we are beginning to ask ourselves, is whether these facade fires have become an unavoidable feature of modern architecture, and whether this is something that we need to be able to live with. Now, clearly, this type of failures are nothing we want to have, and therefore, accepting that we're going to be living with this type of failures is truly a defeat of our capability of technically solving what it is, a technical problem. So the question really is, why are we back to the 1970s? And this is another building called the Joelmas that happened again in the 1970s, just a few days apart from the Andraus fire. And again, very similar type of event. So as I say, in the 1970s, we used to have a lot of this, but we apparently solved the problem. Now, what we need to really ask ourselves is how we lost control of the problem, and it is all about drivers and constraints. So what is driving our construction industry, and what are the constraints that are there to guarantee that society has a level of safety that is acceptable? We cannot really underestimate how much safety underpins well-being in society. And the problem is that many times we almost assume that because we've put in place a certain set of constraints, many times as they're known as building regulations, that these constraints are capable of ensuring our safety. But what we don't recognize is that sometimes the drivers of the industry put us in a position where those constraints are no longer the kind of protection that we expect. So what are the drivers? The driver is energy. So we have a parameter that we can actually quantify. We can measure the heat transfer through walls. We can measure the consumption of energy. And therefore, we can set energy conservation targets. And then those targets can be imposed on people. We can create mechanisms to support the development of technologies to meet those targets. We can introduce subsidies to try to meet those targets. And as such, we develop charts like the ones that you see there that show what is our energy consumption, so we can have a target of reduction of energy consumption. We can talk about space heating, we can talk about many, many different aspects of the way in which we consume energy, and we can set quantifiable targets of performance. So at the core of being able to achieve objectives is our capability to be able to quantify performance. If we quantify performance, we can set targets and we can establish if we have met our targets. So in the built environment, we've set all these targets, and those targets need to be met. And therefore, we are going to provide all the mechanisms to be able to encourage people to meet the targets. We've heard this in the last few weeks with COP26. We want to create all these targets, that relate to embodied carbon emissions, increase in temperature. All these things are basically quantitative targets that enable us to actually develop mechanisms that allow us to achieve or demonstrate that we have achieved those targets. So what follows is a significant investment in developing different technologies, different products that will actually allow us to meet those targets. So once we set the targets, then governments set up vehicles or mechanisms that actually can enable science and technology to evolve to meet the targets. So for example, in the case of energy consumption reduction in the built environment, we have developed and incentivized the evolution of technologies that actually deliver systems that reduce energy consumption. So for example, if I look at this chart, the investment in polymer science, for example, has increased dramatically. And we see that we've developed new materials, new products, complex diagnostics, methods to assess performance, new construction methods, new design methods. Below is the National Science Foundation in the United States, the European Research Council, EPSRC in the UK, the Australian Research Council, Hong Kong, and so forth. And you can see that this is in the hundreds of millions that have been poured in the last decade to try to support the development of these new systems and in these new products that eventually have made it to market and have ended up in our buildings. So this massive investment has enabled to develop the science and the technologies to achieve the objectives or the targets of quantifiable performance associated to the reduction of energy consumption. Now, in parallel, we have liberalized legislation. And why have we liberalized legislation? Because we want to create a space for these new products to enter the market. So now that we have put the investment in developing these products, then we have to smoothen their entry to the market. Now, a very common mechanism to try to smoothen the path to market is by using ambiguity in the legislation in such a way that competent professionals can establish if the system, a novel system, something that is unique, that is just being developed, can actually be used in an adequate manner. So as you can see, when it comes to external fire spread, our legislation or our building regulations establish in requirement B4.1 that the external walls of the building shall adequately resist the spread of a fire over the walls and from one building to another. So it is the duty of the competent professional to interpret the word adequate in such a manner that they can deliver the desired performance for the building. Now, some people believe that actually it is inappropriate to use ambiguity in building regulations, and that is unfortunately not correct. Ambiguity is an appropriate thing. The only problem with ambiguity is that the more ambiguous you make your legislation, the bigger the guarantees you have to make of competency. So the onus of ambiguity is on competency. So to be able to have a proper interpretation, then you need professionals of a higher level of competency. So the two things are together. So you invest, that creates new technologies. To smoothen the path, you introduce ambiguity, and that ambiguity has to come with competency. So as you can see, you're building up a chain of events. And a chain of events enables the drivers, to enter the market. So how does that happen? So you invest in research that leads to new developments. These developments are assessed by competent professionals who take advantage of the liberal, ambiguous legislation to reach positive outcomes. Now, those positive outcomes result in societal benefit, and that is a virtuous circle that eventually encourages society to invest more in research. So as you can see, there is nothing wrong, with what I just described. It is all, if maintained within the sequence, it will lead into a virtuous circle that leads to constant improvement of what we're doing. The problem is that you need also to account for the constraints. In other words, the interpretation of the building regulation, which is the constraints, is the key problem that we need to address. So let's look at the building envelope and energy conservation and see how that actually changed the way in which we do things. So the building envelope is what we changed. It was driven by new construction methodologies that introduced flammable insulation materials. Why it introduced flammable insulation materials? Because if we retain the more conventional non-combustible insulation materials, it became difficult, many times impossible, and definitely impractical to actually achieve the objectives that we have set for the reduction of energy consumption. So if you use a mineral wool or something like that, you will need a lot of weight. There's difficult installation. It occupies a much more significant space because you need a much thicker system, and they don't actually have the stiffness that you will get, for example, with a cellular plastic. Cellular plastics are easy to install, they're very lightweight, they have very low thermal conductivity, and they're obviously very, very lightweight and very easy to install, and therefore very cheap. So in principle, flammable insulation became a very strong participant in the market, and in 20 years, it went from basically no presence in the market to pretty much dominating the market by the time Grenfell Tower happened. Now, how did we manage to introduce flammable insulation materials? The first thing that we did was try to use fire retardants. So we developed all sorts of technologies. There was a very significant investment in fire retardancy in the early 2000s. We went as complex as introducing carbon fibers, nanoclays, all sorts of things. But we very rapidly realized that it was not enough. These materials, no matter how much fire retardants we put in, they were still going to burn, and therefore they will still need to be improved. Now, what was the solution? And the solution was very interesting, which is the concept of encapsulation. So basically what we did is we decided that given that we could not make the material sufficiently non-combustible, what we had to do was to cover it up with a layer of non-combustible material. And so if you encapsulated the material with non-combustible materials, then you will basically result in a non-combustible composite system. okay? Now, that's the process. Now, what was the result? If you look at all these buildings, social housing developed in the 1960s and 1970s, all made out of concrete, extremely poor when it came to energy consumption, massive energy consumption in these buildings. From one second to the other, this is what you had. All these buildings were recladded by the use of very different type of systems that enabled, as you can see from the image on the bottom left, to save cash and stay warm. In other words, meet the quantifiable targets of energy performance. So this happened very rapidly, and Grenfell Tower was one of those systems. This is on the right, Grenfell Tower before the retrofit. This is on the left, Grenfell Tower after the retrofit. So now, if we look at the systems, we used to have a concrete wall. What we have now is a very complex system that if I take a snapshot of it, you will see, it has combustible insulation, polyisocyanurate PIR. It's going to have mineral wool fire barriers to try to control the progression of the fire in the combustible materials. It's going to have an aluminum composite cover, which is basically a sandwich of encapsulated polyethylene that is flammable and is encapsulated by 2 layers of aluminum. And it is all assembled in an incredibly complex system that is of ease of installation. It meets moisture management, multifunction. It does a million different things, but introduces a very, very, very high level of complexity. I believe that the Grenfell system has something like 128 moving parts, that they all have a purpose, and they are used to try to create a system that is actually cheap and performs according to the energy reduction requirements. The problem is that when it comes to fire safety, then how do you quantify performance of the system? Now you have a very complicated system. Now, and it is very important because one of the things that is extremely important in the fire safety strategy of a building is that we rely very much on retaining the fire in one floor. We detect the fire and we warn the occupants. The occupants in the floor of the fire will travel by means of adequate travel distance to a protected space, which is the stairs. And compartmentalization will protect everybody else. So everybody else stays in the building. So in residential buildings in the UK, you have what is called a stay-put strategy. And the stay-put strategy basically requires for everybody to stay in the place while the firefighters fight a one-floor fire. So the fire brigades are going to do what is called defend in place, which is everybody stays put, and they will defend by attacking the fire in a one-floor fire. So their systems are also geared to try to fight a one-floor fire. So what happens if compartmentalization breaks? And then all of a sudden, the fire starts burning in multiple floors. The problem is that if you're going to have a residential building with a stay-put strategy, adequate therefore means no. So you have to retain compartmentalization because you cannot afford the fire spreading beyond one floor. Now, here's 2 fires. On the top, the Shepherd's Bush, a year before Grenfell, and the same crews attended both fires, but the 2 of them have completely different consequences. One of them was retained in one floor, and firefighters came in and solved the problem quite rapidly. The second one allowed the fire to spread, then resulted in the deaths of 72 people and the total destruction of the building. So the question is it possible for firefighters to identify when this will happen? And the reality is that they don't. This is the working environment for the firefighters. And if you look at it, it's a very hostile environment. And if we don't disclose the appropriate information, they will not be able to do their job properly. So all comes back to firefighting operations. They come back in, and we have to have performance criteria that enables the firefighting operations. So if we don't disclose what is going to be the rate of spread, then they will not be able to do their job. If the answer is no fire spread, one compartment, they have protocols, procedures, everything that enables them to do their job. But if we don't give them the right information, then clearly they will have no procedures to be able to conduct their job properly. So as you can see, all of a sudden you've made a series of decisions that have resulted in a situation that has completely disabled your fire safety strategy. So what has changed? Well, this is the Aqua building in Chicago, and you see the conventional approach. You have a concrete slab that protects you from the fire. That concrete slab can be designed appropriately to control the fire and keep it in one floor. And if you made the walls non-combustible, then all of a sudden you have a system that will not fail and will contain the fire in one floor. Now, the problem is that when you have fins of concrete that come out, concrete has a high thermal conductivity, and therefore this type of buildings are not energy efficient. So we changed the paradigm and we created a building envelope. Here you have the Gherkin here in London, and you will see that what we did is we reseeded the concrete slab. We put insulation to separate the concrete slab from the building envelope, and we create a lightweight structure that we're going to hang from the building. The result is that we went from this to this. Okay, and this is really the change. Now, how is this different? So this is a Trump Tower, and as you can see, the fire never progressed to the floor above. Now, obviously, the window is broken here because the firefighters broke it to make sure that there was no remnants of fire, but you can see that the fire never progressed to the floor above. And examples like that, we have many. This is a John Hancock building, same vintage. And again, the same thing, big fire happens, stops in one floor. Now, with these facade systems, these building envelopes, we have totally changed the problem. Now we have a system with a big concrete slab that is connected to a very lightweight system by means of some complex bracketing or some complex fixation system. Now, we need to be able to protect the gap. So now we have a gap between two systems that can actually move freely. One is very lightweight, the other one is very heavyweight, and therefore there is going to be a lot of relative displacement. And the result is an infinitely more complex system that if it includes encapsulated combustible materials, then you're going to have a much more complex problem to deal with. You're going to start dealing with issues, for example, of relative displacement and detailing. So, for example, in this system that you have here, you can see that the concrete slab faces the glass. So this system will never work. No matter how much protection you put in here, this system will never work because the glass will break and then the fire will breach the compartment. So this is a gap that cannot be protected, and that level of construction detailing now becomes a key factor in the performance of the system as an ensemble. So these systems are incredibly complex. They have multiple components, and they are multi-purpose, so they have to fulfill numerous performance requirements. So fire is only one of them. Now, they depend on labor and skill, and therefore tolerances, installation, all these things become very important. And of course, encapsulation becomes the objective because we're using combustible materials that need to be encapsulated to guarantee that compartmentalization is maintained. Now, if you look at this, these are the types of systems. Here you have an insulation encapsulated by an aluminum foil. Here you have the aluminum composite panels like the ones that were used in Grenfell with polyethylene in the middle and aluminum at both ends. And here you have all sorts of other types of systems. And this is what we find today very commonly in buildings for the purpose of managing energy consumption. So the problem is that encapsulation is a mechanical problem and it can fail in many different ways. So if you look at the one in the bottom, you will see an insulation panel with a ceramic rendering that as soon as you start heating it up, you will get mechanical failure of the ceramic rendering, which eventually leads to the ignition and subsequent burning of the material. On top, you have an aluminum composite panel where you're going to see the aluminum separating from the polyethylene, exposing the polyethylene and resulting in the ignition of the system. So you can see how it separates now. And then as soon as it separates and produces a gap, then you're going to get ignition and the burning of the material. In this case, the polyethylene actually drips, it melts and drips, propagating the fire downwards and upwards. So as you can see, you change the problem. And now it is about the mechanical failure of the protective layer. It has nothing to do with the flammability of the material. So again, it is encapsulation really what we need, to assess. And this is where we need to put science into understanding how do we establish the performance of the systems. Now, if I go back to the theory, and I can get you into a lot of detail on this, but this is just a very simple representation of flame spread. If I want to look at the flame spread over a combustible material, it depends on multiple parameters. It's going to depend on the heat of combustion of the material, how much oxygen I can bring to the combustion process. Is going to depend on the thermal properties, ignition temperature of the material, heat of pyrolysis, and a term of losses that incorporates the whole energy exchange in the material as a function of the burning rate. Now, you can come up with different forms of solutions, and you can see, again, it incorporates velocities, densities, Reynolds numbers, characteristic length scales, all sorts of terms. Okay, so these are not simple problems. This is not just common sense. This is a very complicated problem. Now, when you get a system with multiple layers, multiple materials, multiple components, then all of a sudden, the problem increases exponentially in its complexity. So, nevertheless, if we look at the testing methods, the approaches that we use, everything that we have available, they're of a level of simplicity that is actually extraordinary. And that level of simplicity only determines one term, which is the heat of combustion. All the other terms that I have shown before are completely ignored by our current legislation, and therefore our capacity to assess performance is actually negligible. So right now, our regulatory system has no capacity to assess the performance of these very complex systems, despite the fact that they're being used in a generalized way. So in the meantime, here's a very simple list that I got from EPSRC of different projects that have been funded in the last 10 years to try to look at the development of new materials. So in other words, we're putting millions still to create new materials, new methods to development, new methods to characterize them, all these things. So in a way, we are investing in making the challenge even more complex. But at the same time, despite the fact that we have challenged everything by means of complexity, from design principles all the way to our definition of competency, our investment on performance assessment remains zero. In the last 5 years, EPSRC has not invested a penny on trying to help improve the way in which we assess performance of the systems, despite Grenfell Tower. So where do we land? Instead of the virtuous circle, we land in a vicious circle where we don't invest on research. We have no new developments in assessment of performance. We're not training people to be competent enough to understand the complexity, and therefore they're misusing the liberal legislation. The result is very negative, and therefore you land in social inequity, which effectively renders you in a vicious circle. So right now, for the kinds of complexity that we have and for the systems that we have, there's an enormous reliance on competency to interpret our ambiguous legislation, and we are not producing the competent professionals that are capable of doing so. So why does it lead to social inequity? Very straightforward. Here you have two buildings, social housing to the left, Park Avenue in New York to the right. So if I'm going to develop social housing, and I use the regulatory system or the constraints that I have that require very large levels of competency to interpret the ambiguity with these complex systems. And what I'm doing is a social housing project that has small quality, low quality architectural firm because the budget was very low. The engineering budget was very low. So most likely the engineers that you used were very inexperienced. You're going to be using a very standardized design. So approvals are done in a mass manner without very much care. And of course, at the end, because of the low budget that you're exercising everywhere, you're going to end up with a very poor quality building that is inherently unsafe. On the other hand, if you are designing multi-million-pound apartments, then you're going to hire the best possible architect, with all the leading knowledge. You're going to hire the best possible engineers with all the leading knowledge. And because these are unique buildings, what you're going to basically have impose a very large review budget. So you're going to put lots of resources to the authorities to review these very complex buildings. So the process is infinitely more rigorous, and you're taking much greater advantage of the legislation as it is when you have a high budget project. In other words, you have much greater chances of having a high quality, safe building. That, from my perspective, is the definition of social inequality induced by a system that doesn't value the knowledge necessary to assess safety performance. So to wrap up, at the end, it is the wake effect. So when you develop new technologies, when you have new drivers, this is the boat, you have to recognize that you're leaving behind you a very, very large wake. And you don't want this to be the unintended negative consequences of your actions. So only a healthy balance between drivers and constraints can enable science to foster equity. And that's the final message I would like to leave you with. And here we have an example of the reduction of energy consumption as a contrast to maintaining the fire safety of buildings. Thank you very much. Happy to answer any questions.
Thank you very much, Jose, for a very illustrative presentation, and also raising a very important question of first, our ethical duty as engineers, as scientists, to be able to solve problems of the society and to make it equal for everyone, no matter their backgrounds. And I think that you have established a very interesting relationship between that for a building to be energetically efficient, but also how that affects its safety. As I said earlier, we have the Q&A box open for your questions. We have a couple of them already. Feel free to keep sending them. Otherwise, if you want to raise your hand, as I can see that there is one already, we will allow you to talk. So let me ask you first, the question that was posted to the Q&A box, it was asking if you could elaborate what are the competencies required to respond ambiguity, and does that mean skills, capacities, and resources?
Yeah, I mean, I think that this is a very, very interesting question, and it's at the core of the problem that we have. Now, the problem that we have right now with fire safety, that we have not made a clear definition of competency. If you think about it, in most professions, you have accreditation processes, and in many ways, you guarantee professional competency through education, tertiary education, receiving a degree and then going through a process of certification. That unfortunately doesn't really exist in fire safety, where the tertiary education is very limited. There are no accredited programs in fire safety engineering, and the professional organizations that in principle are there to represent fire engineering are not necessarily populated by people that exhibit those level of competencies. So I think fire safety engineering is a complex engineering discipline, and as such, professionals practicing fire safety engineering should be competent professionals that are certified as such. Now, the knowledge that is necessary is really interesting, because at the end, at the core, the knowledge that you need is to be able to design and assess the performance of a fire safety strategy. Now, because it's such a broad discipline, that is going to require you to invoke the expertise of, for example, people doing computational fluid dynamics, people doing heat transfer analysis, people doing egress modeling, all these other tools that are part of a design team will contribute, to the fire engineer to be able, to this professional to actually stitch everything together into an appropriate fire safety strategy that meets the intent of the building regulations. So in principle, we need to define the profession. We need to define clearly what those skills are and implement a system that enables us to certify those professionals accordingly.
Thank you. We have another question from our head of department, Yanis. Would you like to ask?
Yeah, thank you. Thanks for the great talk, Jose. I understood that at some point, I appreciate that this may be a naive comment. I understood that at some point you said that there is a lot of investment happening on solutions that will increase complexity as far as the defending against this problem. But isn't there, given the size of this market and the importance of what's happening, isn't there great scope for invention, for a purely inventive step of a brand new material that satisfies the requirements, something that's very light, cheap, completely inflammable, high insulation capacity? If such a material existed, it would be a simple and definitive solution, right? And I'm surprised with all this stuff that's happening in material science that this has not happened, or we don't have something like that coming our way.
Yeah, no, and I think you're absolutely right. I think the truth is that having these systems that rely on hundreds of parts and are incredibly complex are bringing us to a position in which we have to really elevate the level of knowledge to be able to assess the performance. They're obviously much simpler solutions that should and could be put in place. The problem is that to be able to develop those solutions, you have to change the mindset of people. You see, if you think about how the polymer industry develops materials, the way they do it is they develop a material that covers all the necessary functionalities. And then they think that the way by which you achieve fire safety is you benchmark against a very simplistic test. So the best possible answer that you can get is you don't have to change your material and you don't have to invest an extra penny on it. And the test has to be very fast throughput, okay? And it has to be incredibly simple because we don't want to waste any time. Our product is ready. We've met all the other functionality requirements, and fire is just this last hassle that we need to get through. So until we start promoting integrated and optimized design that includes fire safety as one of the variables of optimization, we're going to continue to design materials that are great for everything and terrible for fire. And then we have to introduce all these barriers of protection and all these different things just to make sure that we can use them. But the reality is that if we actually change the way in which we think, and our governments and our funding agencies change the way in which they think, and started investing in a more comprehensive optimization process, we will probably come up with brilliant things.
Thank you.
Thank you. Yeah, it's very sad that it has become a ticking box exercise, the fire safety, rather than one of the priorities. We have another hand raised from David Andrews. Would you like to talk?
Sorry, just get me unmuted. Can you hear me?
Yes, we can hear you.
Excellent. Thank you very much, Jose. Fascinating. I obviously come from a related industry, which is the shipbuilding and shipping, where we had a classic example of a very similar sort of situation, which was to do with ro-ro ferries and the introduction of ro-ro ferries, which were said to be highly efficient. But when it was pointed out that they were actually dangerous, both the industry operators and government ignored the professionals. And we subsequently had a series of catastrophic ships that failed very rapidly. And that was the rapidity of their that they turned over, which was the issue. I was going to just raise the issue sort of to me, you emphasize quite strongly science. To me, science is about truth. And to a degree, despite Oppenheimer, there's a certain amorality about searching for truth. Whereas engineering, to me, is about doing things efficiently. And the big question is what you mean by efficient. And we do emphasize that ethics matters in engineering. Having said that, in my field, we still allowed ourselves to be involved in building ships that were unsafe. So it seemed to me that if you think about the market is inevitably going to be uncontrolled unless it is regulated by government and indeed insurance. And I'm surprised the insurance industry hasn't been more effective because frankly, government hasn't been effective. It's government that actually built those unsafe buildings as cheaply as they possibly could for in the case of Grenfell Tower and the like. So I wondered why perhaps in your field the insurance industry hasn't been stronger.
Yeah, no, this is a very interesting point that you make, and I do agree that there is a slight nuance between science and engineering that needs to be considered carefully. But so just to explain a little bit the process and so without trying to be too controversial, the problem with the construction industry is that the government in its expedience to try to support and sort of foster the growth of the construction industry. We underwent not only a process of deregulation, but also the government exercised on itself a frontal lobotomy. So the moment, the moment that the government got rid of their brains, yes. When it came to decision making. So the government used to have the building research establishment that effectively represented the science or the engineering base on which the government was informed to make decision. Now they made a decision of privatizing the building research establishment, which was effectively a frontal lobotomy. So they took the brain out and they subject the brain to commercial market forces, which effectively made the building research establishment a much more complex organization that actually was servicing many masters and not only the interests of government. So the moment that you did that, all of a sudden then decision making started deteriorating. And the result is that decisions that were being made became more and more and more and more incompetent. And all we have to do is watch the videos from the Grenfell Tower inquiry, and you will see it. I mean, the evidence of the completely generalized incompetence, at all levels is exceptional. So, but I really think it is a product of where the regulator stopped understanding the problem that they were regulating, and then all of a sudden, just basically, what we see is the result of that. And Dame Judith Hackett in her report explained that very well. And she said it was the race to the bottom, basically.
Yes. Thank you.
Thank you for that explanation. Yeah, it's a snowball becoming bigger and bigger. And when we don't understand well the points of failure of what we have designed, or some people that should have that understanding don't put it in place, the regulations for that. We have reached the end of the webinar, but thank you so much, Jose. It has been extremely inspiring and illustrative, also making us to question if we are doing all that we should be doing, but it has been very good to have you with us.
Well, thank you very much for having me. I mean, it's been really a pleasure, and thank you for the great questions.
Thank you. Just to say that this talk will be available in our MECENG website in some time, but in the meantime, anyone interested in having access to the Zoom link recording can email me. I have put it in the chat, my email, so I can share it with you before, if you would like to. And with no more delay, Janice is giving you an applause, and it's very well deserved. Thank you very much for everyone, and I hope to see you in our next webinar. Thank you.
Thank you.
Bye.
Bye.